Parallel resonance. So in parallel resonance, resistor, inductor and capacitor are connected in parallel, and this combination is connected to a voltage source. Now there is a current coming from the source. That current is divided as into the elements. So here elements, resistor, inductor and capacitor are the elements. Current in the resistor is IR, the current in the inductor is IL, and the current in the capacitor is IC. So if you apply KCL at this node, I is equals to IR plus IL plus IC. So I is equals to IR plus IL plus IC. So IR can be written as, so V by R. IL can be written as V by JXL. So JXL is the reactance offered by the inductor, and similarly capacitor. So reactance offered by the capacitor is XC, and current IC is equals to V by minus JXC. Current in the inductor is V by JXL. Current in the resistor is V by R. So because V equal to Ri and V equal to JXL into IL and V equal to minus JXC into IC are the basic relations. So here I is equals to IR plus IL plus IC. So I is equals to V by R plus V by JXL plus V by minus JXC. So if you take minus sign into the numerator, so here next step is, so current, so you can take voltage as common in these three terms, and taking that voltage to left hand side you get current by voltage. So current by voltage is nothing but admittance. So admittance offered by the circuit is equals to current to voltage ratio, which is equals to 1 by R plus minus J by XL plus J by XC. So Y is equals to, admittance is indicated with the Y is equals to 1 by R minus J 1 by XL minus 1 by XC. So Y is equals to, it is a complex number, admittance is a complex number, and the real part is Z and imaginary part is B. So Y is equals to Z minus JB, where G is conductance and unit is mho or Siemens, and B is called as susceptance and unit is say mho or Siemens, and Y is admittance. So here Y is admittance, G is conductance and B is susceptance. So here Z conductance is equals to 1 by R and susceptance is equals to 1 by XL minus 1 by XC. So admittance is equals to magnitude of the admittance is equals to root over 1 by R square plus 1 by XL minus 1 by XC whole square. So let it be equation 1. We know reactance offered by the inductor XL is equals to omega L, which is equals to 2 pi FL. So but here in parallel resonance we want expressions for 1 by XL and 1 by XC. So that's why 1 by XL is equals to 1 by 2 pi FL, which is equals to, so 2 pi L is a constant. So that's why 1 by 2 pi L I am taking that as some K constant. So 1 by XL equal to K by F. So if you take this F2 left hand side of the equation, you get F into 1 by XL equal to K. So here we have to draw a curve between 1 by XL and F. So F is on the x axis and 1 by XL is on the y axis. So here it is in the form of xy is equals to K, which is a rectangular hyperbola. So we get a rectangular hyperbola curve. So frequency on the x axis and 1 by XL on the y axis. And similarly XC is equals to 1 by omega C, so which is equals to 1 by 2 pi FC. But here we want, in parallel resonance we want 1 by XC curve. So mathematical expression for the 1 by XC. So 1 by XC is equals to 2 pi FC, which is equals to 2 pi C is a constant K and F. So 1 by XC is equals to constant into F. So it is looking like Y equal to mx. So it is a straight line passing through the origin, frequency on the x axis and 1 by xc on the y axis. So after that V is equal, so what is the relation between voltage, current and admittance? So voltage is equals to current by admittance. So this is equation 4. Now let us try to draw the graphs for against frequency. So 1 by R against frequency, 1 by XC against frequency, 1 by XL against frequency, mod Y against frequency, and mod V against frequency. So these are the different curves which we have to draw in parallel resonance. So 1 by R against frequency. So if we draw the 1 by R against frequency, 1 by R is a constant. It is independent of the frequency. So you get a straight line parallel to frequency axis. So this is 1 by R curve. So 1 by R against frequency. So after that, if we draw 1 by XL against frequency. So 1 by XL against frequency. So here we get a rectangular hyperbola. The curve between 1 by XL and a frequency is a rectangular hyperbola. So this is the curve. So here this is the curve. So as the frequency is equals to 0, 1 by XL equal to infinity. At a frequency equal to infinity, 1 by XL equal to 0. So in between, 1 by XL curve starts at infinity and goes to 0. It is a rectangular hyperbola. Next curve is 1 by XC. So 1 by XC against frequency. So here we get this, it is a straight line passing through the origin. So this is the 1 by XC curve. Next is modulus of Y. So modulus of Y is root 1 by R square plus 1 by XL minus 1 by XC whole square. So if you draw a curve in between mod Y and frequency, so this is the curve. So it starts at infinity, comes to 1 by R and again goes to infinity. So at frequency equal to 0, mod Y is infinity. At frequency equal to FR, which is a resonance frequency, mod Y is equals to 1 by R. At frequency equal to infinity, again mod Y equal to infinity. So next is mod V, so which is a voltage across the elements. So against frequency. So frequency on the x-axis and mod V curve. So at frequency equal to 0, voltage across the circuit is 0. At resonance frequency, maximum voltage is there across the circuit. And at again infinity frequency, so voltage across the circuit is 0. So here we get at a resonance frequency, we get a maximum voltage across the circuit. And 1 by root 2 times of the maximum voltage is this point. So draw a dotted line which cuts the mod V curves at 2 points. And the corresponding frequencies is said to be cutoff frequencies, lower cutoff frequency and upper cutoff frequency. So F1 is the lower cutoff frequency and F2 is the lower cutoff frequency. So at resonance frequency, voltage across the circuit is maximum, V max. And at cutoff frequencies, voltage across the circuit is 1 by root 2 times of the maximum value at resonance, or otherwise 71% of the maximum value at resonance. So the distance between the cutoff frequencies is nothing but bandwidth. So now let us try to derive the mathematical equation for the resonance frequency. So what is the condition for the resonance? So at resonance, imaginary part is 0. So here susceptance part is 0. B equal to 1 by XL minus 1 by XC is 0. So reactance part of the admittance is 0. So here admittance, reactance part of admittance is susceptance. Real part is conductance. So 1 by XL, B equal to 1 by XL minus 1 by XC is 0. So 1 by XL equal to 1 by XC. So which is equals to XL minus XC. So XL is equals to that resonance. So XL equal to XC. So omega L equal to 1 by omega C. So at resonance I am taking, instead of omega I am taking omega R. Omega R L equal to 1 by omega RC. So omega R square is equals to 1 by LC. So omega R is equals to 1 by root LC radians per second. In terms of hertz, FR equal to 1 by 2 pi root LC hertz. So this is the condition for the resonance. So resonance frequency, at which frequency the circuit is resonance means 1 by root LC radians per second. In terms of hertz, it is 1 by 2 pi root LC heads. So next is, so what is the admittance at resonance frequency? So what is the admittance offered by the circuit at resonance frequency? So mod y is equals to 1 by R. And what is the voltage at resonance frequency? Voltage at resonance frequency is mod V equal to I by mod y, which is equals to mod y is 1 by R. If you take that R to numerator, we get Ri. So what is the voltage across the circuit at resonance frequency means Ri. So here bandwidth is difference of the cutoff frequencies. Bandwidth equal to F2 minus F1, where F1 is equals to lower cutoff frequency and F2 is higher cutoff frequency. And what is the quality factor of the circuit at resonance means Q is equals to ratio between resonance frequency to the bandwidth. If you know resonance frequency and bandwidth, ratio between the two is nothing but quality factor of the circuit. So these are the important points for series resonance. So here resistor, inductor and capacitor are connected in parallel, and what is the condition for the resonance and how the graphs. So graphs means 1 by R against frequency, 1 by XL minus 1 by XL against frequency, 1 by XC against frequency, mod Y against frequency and mod V against frequency. That are the important curves which we have to draw in parallel resonance.